This is Lab 1 charge tapes. In this lab, we're looking at the behavior of two charged tapes, tape A and tape B, in regards to their electric fields and forces in order to determine the amount of excess charge in the tape. So what we did in the experiment was take charged tape A close to a hanging charged tape B, and then found the distance between the two once the repulsion occurred between the two tapes. We found these results for our lab, which I'll be going into further later on in the presentation. So we used the fundamental physics principles of electric charge interactions where opposite charges attract, like charges repel, and charged objects attract neutral objects. We also use the fact that an electric field surrounds a point charge and exerts forces on other charges in the field. So in our case, tape A was our point charge and exerted an electric force on tape B, which was in the field. So the electric force was the force exerted between tape A and B, and we used this formula to calculate charge in our tape. To determine the sign, first of all, we used our knowledge of interactions, and we found that the sign of the tape would be positive because it's attracted to a negatively charged plastic pen. We also know that there's an electron deficiency in the tape because the positive charge means there's a lack of electrons in the tape. A few assumptions we made to find the amount of charge on tape B was we ignored air resistance, we treated the tape like it was a point charge, and all the charge was concentrated at the center of the tape, and we assumed that each tape made had about the same amount of charge evenly distributed along the length of the tape, because we made both the tapes in the same way. To do the charge calculation, we saw that there were two forces acting on the top tape in the y direction, the electric force and the gravitational force, and we knew that F net in the y direction would have to equal 0 because there's no change of momentum in that direction. And we used the length of the tape and found the weight of the tape using our conversion factor, and also found the distance between both tapes after their repulsion from the interaction occurred, and plugged that into our formula using the assumption stated before, and we found our charge for our tape B to be 6.12 times 10 to the 10th coulombs. We also can see that the magnitude of our gravitational force and electric force are equal. Using our charge tape of B, we divided that by a singular charge of electron to find the electron deficiency in the tape, and we found that to come out to 3.83 times 10 to the 10th electrons, and we also found the number of electrons on tape B by using the conversion factor 1 atom per 1 times 10 to the negative 10th meter, and that all came out to be 3 times 10 to the 16th atoms. And then using these two values, we found the electron deficiency per atom in tape B to be 1.28 times 10 to the negative 6 electrons per atom. We also use GlowScript to model the real system. So our point charge representing tape A was modeled here, and then our point charge for tape B was modeled here using this piece of code. And I used a function to calculate E field, so that took in source charge and the observation location, which in this case was the source charge being tape A and the observation location being tape B, because the tape A had an electric field that was causing this electric force on tape B to be created. So we found the electric force on tape B using these values and made an arrow to represent that quantity. We also made a gravitational vector to represent the gravitational force, and we found that the magnitudes of both of those were equal, as supported by our calculations from before. So what if the electrons had a positive charge and the protons had a negative charge? Well, if the charges flipped, the same interactions would occur because the interactions are still happening between like charges and unlike charges, regardless of the name of whether if it was proton or electron. Also, why is it important to handle the charges on the tapes as little as possible? Well, that's because it's important since the charge on the tape could transfer elsewhere. If the charged tape comes in contact with other things, it could discharge and then not exert electric force. Overall, we were able to find these values, and our GlowScript code connected the relevant physical principles to the model used to represent the real system. It showed how the forces would look and confirmed that the electric force on tape B, created from the electric field from tape A equal the gravitational force on tape B in order for it to float.